Sound is a mechanical wave. So speed of sound depends on type of the medium. One of them is that. Second one is temperature of the medium. So first we will talk about this type. Speed of the sound wave normally defined how quickly one particle transfers its vibration to another particle. So normal wave means transferring vibration. We know about that. If vibrations transferred very quickly, so then you can say that, yeah, speed of the sound in this medium is great. But if vibrations transferred slowly, so in this case, you can say that, yeah, speed of the sound in this medium is small. So then this is about how particles are close to each other. If they are so close to each other, so in this case, vibration will be transferred quicker. But if the particles are farther from each other, the molecules are farther, in this case, transfer of the vibration will be late. That's why solids, particles of the solids are so close to each other compared to liquid and gases. For that reason, sound travels fastest in solids, faster in liquids, but slowest in the gases. So this is a table how speed of sound changes in gases, it's air, in liquids, and in solids. For example, in air, 25 degrees air, 60 degrees Celsius air, it is 346. Like seawater, it is 1,530, almost 5 times. So 5 times faster speed of sound compared to the air. But solids, look at this one, aluminium 5,100, copper 3,560, iron 5,130. So if you compare these two, almost, I think, 15 times, almost 15 times greater. So that's why in solids, the sound travels fastest. In liquids, a little slower compared to, slower compared to the solid, but gases, in the gases, because molecules are very far from each other, vibration transfer is late compared to the others, so then in gases, slowest. You don't need to know these numbers by the time, though, if you are wondering, you don't need to know. Just I put this table to make comparison. Because molecules of the solids are closer than the molecules of both liquids and gases, solid responds to the disturbance more rapidly. This makes that sound is fastest through solids. And as I said, second factor is the temperature. We know in chapter 3, section 3, we learned about this. Temperature of the medium increases. In this case, particles are starting to vibrate with a longer amplitude. Speed of sound in gases changes with temperature, because as temperature rises, amplitude of the vibration increases. Amplitude of the vibration means this. So initially, every particle vibrates, but when it's cold, particles vibrate in a shorter amplitude. But it is getting old. Temperature increases, amplitude of the vibration becomes greater. If you increase the much more, then in this case, amplitude becomes much greater. So that's why as amplitude increases, I am giving an example like this. Think about a classroom. There are 20 students. All are standing without vibrating, without moving back and forth. No one collides. But if they start vibrating back and forth with a smaller amplitude, there could be some limited number of collisions between the students. But if they vibrate with an amplitude of greater amplitude, this time, number of collisions between students will increase. It is the same as for the molecules. As temperature increases, amplitude of the vibration increases. That's why particles of the gas collide more frequently compared to a gas which is cooler. And for that reason, this causes disturbance to spread faster. So disturbance, wave, can spread faster in gases at higher temperature. But this difference in speed due to temperature change is less noticeable in solids and liquids, because Particles are already so close to each other. So this was ministry exam question of 2017. The question was like this. This change in speed due to temperature is less noticeable in A, solids, B, liquids, C, solids and liquids, D, gases. So which one? Solids and liquids. So difference in speed due to temperature is less noticeable in solids and liquids, but more noticeable in gases. There are tables. You see this table. When air is 0 degrees Celsius, speed of the sound is 331. As air increases to 25 degrees Celsius, it increases 345. But if you heat air up to 100 degrees Celsius, speed of the sound becomes 366. As you see, as temperature increases, yes, the speed of the sound in the air also increases. Sound waves propagate. Propagate means vibrate. But generally for sounds, in physics, this word is used. Propagate. Sound waves propagate, travels. Propagate means travels. Sound waves propagate in all directions, yani in 3 dimensions. That's why motion of sound waves can be approximated as spherical. Maybe you see in animation, in the simulation, that almost spheres are produced by the compressions. You see that these compressions are traveling in all directions. That's why they all make a sphere. If you think in two-dimensional space, like on a piece of paper, if you want to draw that, it becomes a circle. But think about three-dimension. So when I was talking in here, sound is not only traveling in one dimension. It's moving forward, backward, upward, downward, right, left. So in all directions, it's traveling with the same speed. That's why we said that sound waves are expanding about this tuning fork. But as I said, we cannot draw a sphere on a paper. Instead of spherical sphere drawing a sphere, because it's impossible to draw a sphere on a two-dimensional surface, we are going to represent the sound as series of circles surrounding these sources like this. This is one compression. This is another compression. That is third compression. So you are going to draw compressions around the source as circles. Now, this is a sound source. Assume that it's a loudspeaker in here. Of course, this sound source is making some compressions. So we are going to represent compressions in this picture. And compressions, remember, they were the regions of high pressure and high density. These compressions, this is one compression, represents one compression. This is another one. So one after another, there are compressions you are sending as the tuning fork is vibrating. It sends vibrations, compressions. And these compressions are now given a new name, wavefront. Wavefront, like front of a wave. Like front of a wave. So compression, high pressure or high density region is represented by a circle, and this circle is called a wavefront. And this wavefront corresponds to the crest of the sine wave. Remember, pressure wave is changing as a sine wave, high pressure, low pressure, high pressure, low pressure, high pressure. And every compression we know corresponds to crest. Now this compression is given a name, every wavefront. Yes, every wavefront now corresponds to crest of this wavefront or crest of this sine wave. But between two compressions, what is there? There is rarefaction, low density, low pressure region. Between these two compressions, there are rarefactions, low pressure, low density. And we know that every rarefaction corresponds, or every low pressure corresponds to trough of this sine wave. Like here, this is one rarefaction, trough. Another rarefaction, again trough. So rarefaction represents, we know, low pressure, low density. It represents the trough of the sine wave. We learned this before. And distance between adjacent wavefront is one wavelength. It's the same as the distance between two compressions. Yeah, distance between two compressions or distance between two wavefront is called one wavelength. One wavelength. And also we have radial lines which explains or indicates direction of the wave motion. In which direction this wave is moving. So these rays are representing that. Rays are radial lines. Radial lines. When we say radial, you will understand along the radius. A line along the radius is given a name radial. Radial means line along the radius. So as you see, these radial lines are along the radius. This is the radius of each circle. This is the radius of this circle. That is the radius of this circle. So these radial lines are representing in which direction these sound waves are moving, and always perpendicular to the wavefront. Remember, we learned that because if you draw a line in here, so radial line is always perpendicular to tangent. We learned it in chapter 1, section 2 and 3. We talk about this. Radial line is always perpendicular to tangent line. That's why every radial line you draw, every ray you draw here will be perpendicular to wave front. Wave front in here, in here, in here, wherever you draw them. Wavefronts of a small portion of a spherical wave that is many wavelengths away from the source are nearly parallel planes. Such waves are called plane waves. What does it mean? Now I will try to explain. In here, there are so many wavefronts, so many compression points. So this one is early sent, this one is later sent, and after that one, and after that one. So many compressions are sent one after another. But as the wavefront is expanding, if you take a part of, say that only this part, I am going to take this portion of each wavefront. I draw it now. The inner one, the inner wavefront seems to be curved. However, as your wavefront travels away, this curve gets closer to a straight line. As a wavefront moves away from the source, a small portion of this spherical wave can be treated as a plane wave. A part of the spherical wave can be treated as a plane wave, but the wavefront must be many wavelengths away from the source. Many wavelengths away from the source. This is the condition. Next title is about breaking the sound barrier. So in the first one, the airplane was stopped, remember, but the engine is running. So engine is making a sound, and the sound is traveling in all directions. So that's why the separation between wavefronts is not different in all directions. It is the same. So those separations, right, left, up, down, in all directions, in all time, it is the same between the compressions. But when the airplane is flying in one direction, for example, like this one, but with a speed less than speed of sound, it is moving. So I'm going to show it by a animation in here and a simulation. So initially, this airplane in here makes it that it releases a compression, and then this circle represents the compression. And airplane continues moving to the right. But as airplane is moving to the right, this compression is expanding. So it's something like this. So airplane is moving to the right, and by the time the first compression released by the airplane is expanding. And then After some time, so it releases another compression. So as you see, the separation between this compression and that compression, or between these two wavefronts, are not the same in all directions. So it is shorter in a direction which is in the same direction of the motion. It is longer in a direction which is in the opposite direction of motion. And behind it is longer, in front of the airplane it is uh, shorter. It's just another simulation in here showing that, yeah, as you see, when the source is moving in one direction, then wavefronts in front gets closer, but wavefronts behind gets a lot farther from each other. And if airplane flies there at a speed which is equal to speed of sound, yani v airplane is equal to v sound in this case. So again, assume that this airplane first releases a compression, which is a wavefront. So as airplane moves to the right, this compression also expanding in all directions. But this time airplane is moving faster, and then when it releases a second compression, as you see, so at this point at the tip, these compressions coincide and these wavefronts coincides. Of course, when they coincide, so what's going to happen? So it's interference. So that if two pulses interfere, so then they are going to produce a greater pulse, greater amplitude of the pulse. And then there are so many waves, in fact, interfere at this point. Just I draw two of them, but at that point, at the tip, uh, all the compressions interfere constructively, and that's why amplitude of the wave increases in here. And then we know that amplitude makes, if amplitude increases, power of the wave increases. And that's why here is formed a very strong resultant wave. This resultant wave has a very big energy, and that's why it has a very big power, and that's why it has a very big sound. So when airplane attains the speed of sound, disturbance accumulate in front of the plane that increases the amplitude of the resultant wave and creates a shock wave. That shock wave, and this great a wave with greater amplitude is known as shock wave because its power is so huge. What if the airplane exceeds the speed of sound? So in this case, it's going to be like this. So this time, two compressions will also interfere at some points, but not only one point at the edge. One point is here, other point is right here. So that at the edge of the airplane, they will interfere. They will form a shock wave. Simulation is showing like it's like this. Follow here in this simulation, and it's moving now at a speed greater than speed of sound. As you see, and this point in here in this line, all these waves interfere constructively and forms a shock wave. So this shock wave, when this shock wave arrives to this ground, somebody's message, for example, standing on the ground and then watching the airplane, suddenly, as soon as this shock wave reaches his or her ear, so she's going to or he's going to hear a very big boom. So like there's a bombing. So when speed of the plane exceeds speed of sound, the shock wave will form at the edge of the plane. That's the point. In here, the shock waves will form in here because interference is at the edge. In here, so superpose, which means superposition, they interfere and give a very huge power, huge explosion. This is named as breaking the sound barrier. So that speed of the sound, speed of the airplane becomes greater than speed of sound. That's why we say it's breaking the sound barrier.
Watch the vapor build up on this airplane. Look at that. Oh, yeah!
Super Hornet high-speed pass.